Good afternoon, ladies and gentlemen. In the next 15 or 20 minutes, I will speak about the deuterium content of different water bodies. My presentation is not coming to be very comprehensive, but rather I will give you some mosaics from this field, focusing mostly on the deuterium content of water and some other substances in the nature. The content of my presentation, first I will speak about the different parts of the water cycle. Then at the end, I will give you some data of the deuterium content of some natural substances. First, I think you are aware of this fact that the hydrogen has got 3 natural isotopes. Of course, you are aware of the first 2 ones, the protium and the deuterium. But in the nature, there is a third one as well. The first 2 are stable isotopes, while the third one is radioactive. In the isotope hydrology, I work in the field of isotope hydrology, we use the radioactive tritium as well, together with the stable isotopes, because these are very good tracers, natural tracers. We can trace the way of the water, and also we can see what happened with the water. Here I show you the atomic mass units of the hydrogen isotopes and the oxygen isotopes. The water molecule consists of these 2 elements, hydrogen and oxygen. And as you can see, protium has got about mass number 1, deuterium mass number 2, tritium mass number 3, very big relative difference. While in the case of oxygen, oxygen 18, oxygen 16, the relative difference is not so high. So if I calculate the relative difference between the deuterium and protium, it is 100%, very big difference in the mass, and it has a consequence. And that's the reason, while in the case of oxygen, the relative difference is only 12.5%, much less. And if I would calculate it for even heavier elements, it would be even smaller number. So this is the reason that the highest isotope effect among all the elements can be noticed in the case of hydrogen, in the nature, I mean. In the isotope hydrology, we don't use ppm. I will tell you the data in ppm, but in isotope hydrology, we use the so-called delta value, delta D or delta H2O, which was practically introduced by Roman Zubarev in the first presentation. And we express our data relative to the standard mean ocean water. So we compare always to the ocean, because the ocean is a very big water mass, and it is enriched in heavy isotopes, both in hydrogen and oxygen as well. This is the water cycle, how we use in hydrology, isotope hydrology as well. The starting point is always the oceans, world oceans. The water evaporates, gets to the atmosphere, then clouds are formed, and the clouds are moving over the terrestrial area. And if there is a temperature decrease, some part of the water condensates, and it is called precipitation, rain or snow. The water is falling down, and the far majority of the water gets back to the ocean on the surface. We call it runoff water. Few percent is infiltrated under the ground. This is the groundwater, and this is very special, very precious water, because especially in Hungary, the dominant source of drinking water is groundwater. And deuterium content of different water bodies. The natural water contains about from 90 ppm to 160 ppm. It is a rather wide range of deuterium content. And the highest deuterium content you can find in some lakes in arid territories where the evaporation rate is very high. Because during the evaporation, the lighter isotopes preferentially leave the water body and the remaining water enriches in heavy isotopes. So that's the reason that the highest deuterium content you can find in some lakes like Chad Lake, Lake Chad, or Lake Van in Turkey, and some others as well. And the deuterium content is about 160 ppm in these lakes, around this value. The deuterium content of the ocean is 156 ppm, and it is rather homogeneous. It's a huge water body, and homogeneous but not everywhere. Where the big rivers enter to the ocean, on that area, the deuterium content is of course lower. The most depleted water in the form of ice can be found in Greenland, Antarctica, North Pole, and its deuterium content is 90, 110 ppm. You regard it as a deuterium depleted water. Gábor Somjai sell it water as a deuterium depleted one. So on the Earth poles, where there is the temperature is the lowest, you can find the most deuterium depleted water in ice. Of course, it is true for high elevation mountains as well. I will show you later on. This map shows you the deuterium content of the precipitation on the Earth. You can see the orange color shows the highest deuterium content, the blue the lowest deuterium content. So, as I told you, the lowest deuterium content you can find on the Earth poles. And as we start from the equator to the north, gradually decreases the deuterium content. Deuterium in the precipitation in Europe. The highest content, deuterium content, is in the Mediterranean area. And as we are going to the north, the deuterium content is less and less. In the isotope hydrology, we use different isotopic, we are speaking about different isotopic effect, like continental effect or latitude effect, altitude effect, and temperature effect. These are not totally separated effects. Some of them are interconnected. I show you some example. This is the map what I showed you, and we call it latitude effect. At the higher latitude degrees, the deuterium content is lower. This is the altitude effect, with other name is elevation effect. So if we start from the lowland, and we are going upper part of a mountainous area, the deuterium content of the precipitation is lower and lower. So if you go in the high elevation Alps or Himalaya,
recording in progress.
The deuterium content is lower and lower. And this diagram shows you that the highest deuterium content is close to the sea surface, and as we are getting higher and higher elevation, the deuterium content is lower and lower. So this is a elevation effect. What is very interesting that the oxygen isotopic composition and the hydrogen isotopic composition, there is a very good correlation between these two compositions. So, and this is a so-called precipitation waterline, isotopic waterline, with other word, global meteoric waterline. So the precipitation is always situated along this line. If we measure the isotopic composition of a water, and it is not on this water line, it means that something happened with the water, and we have to explain it. And this is a diagnostic tool for reconstructing what happened with the water. Continental effect. Continental effect is that the water evaporates from the ocean, a cloud is formed. Delta O18 is written here, but it is true for the delta D as well, for the deuterium as well. I showed you they goes together. And the first rain has got -3 per mil in delta O18. And because the heavy isotopes are enriched in the condensate, it means that the remaining vapor becomes isotopically lighter. And the next rain, it is -5, little bit more negative, and the vapor is even more negative. And as it is going ahead into the central part of the continent, the precipitation will be isotopically lighter and lighter. So the deuterium content is lower and lower. This is called the continental effect. Temperature effect. These data are from Budapest. I measured the precipitation isotopic composition. As you can see, there is a very high variation in the isotopic composition of the precipitation. There is a significant difference in the summer precipitation and winter precipitation. I calculated the deuterium content in ppm. What does it mean? So in summer, the deuterium content is 152 ppm, while in winter time, when there is snow and very cool, the deuterium content is 132 ppm. 20 ppm difference. So if you could collect the snow winter time, you could get a deuterium depleted water. This is showing you the so-called temperature effect. On the horizontal axis, there is the monthly temperature, monthly average temperature. And the other axis, the delta O18, but this is the same for deuterium. As you can see, as the temperature is higher, the deuterium content is higher. It is true for seasonally within the year, but it is true also if there is a climate change. So especially in Hungary, Hungary is situated in a Carpathian basin, a big basin, and there is a lot of groundwater which infiltrated during the Ice Age, more than 11,000 years ago. And the deuterium content is lower because in that time the mean temperature was lower significantly. So there is a significant difference. This is showing the same temperature and the isotopic composition. And as you can see, different meteorological water station. The correlation is not exactly the same, but the trend is the same. Higher temperature, more deuterium. Summarizing, in Hungary, winter minimum temperature 132-33 ppm. Summer, the maximum is 152. And the water which infiltrates under the surface is just in between and a little bit closer to the winter, because a higher rate of the winter precipitation infiltrates than the summer precipitation, because in summertime the temperature is higher and more water evaporates. This is the last slide about the water cycle. Let's go to the atmosphere and have a look at the vapor in the atmosphere. As you can see on this diagram, that the vapor just over the surface, Earth's surface, has got a very low level of, has got a relatively low level of deuterium, I mean comparing to the water, because you remember that the deuterium is enriched in the condensate. So the vapor contains less, and this is about the vapor. So if you look at the deuterium content of the vapor just over the surface, it is 130 ppm. And as we are going upper and upper part of the atmosphere, troposphere, tropopause, stratosphere, the deuterium content is lower and lower, and not just a little bit lower, but a lot lower. So the minimum is 50, 60 ppm in the tropopause. This is in the atmosphere. Just some interesting feature. we cannot take that vapor. I mean, we cannot collect that vapor, but it is, anyway, it is there. So it is for me, it is interesting. I hope for you as well. So this was the last from the water cycle. And now I show you some data of natural substances, some natural substances. Not much. One is methane. Methane is produced in the nature by different processes, and it has got a rather low deuterium level. Its deuterium level is from 94 to 135 degrees centigrade. So if you burn this methane, the water will have got 94, 135 ppm deuterium. This slide just shows you that there are different processes in the nature producing the methane with really different delta H2, I mean, the really different deuterium content. So if you burn, as a consequence, if you burn this methane, the condensed water, if you can collect the condensed water in the power plants where this methane is burned, then you will get a deuterium depleted water and significantly depleted water. Now, geogenic hydrogen gas. Maybe you have heard about this, the existence of this hydrogen gas. Geogenic means geological hydrogen. The hydrogen gas was what is produced in the nature under the surface. And recently, you can read about it, more and more paper about it, that it exists different parts of the world. And this is called white hydrogen, not green hydrogen. Green hydrogen, when you use the solar energy and you dissociate the water molecule and produces hydrogen gas, that is green. But this is called white, absolutely innocent, because it is produced by the nature itself, and what you have to do is just collect. And really, there are places, different places in the world, when it is emanating, coming up from the Earth's surface. One is in Africa. And what is very interesting, that there is a huge fractionation between the water and the hydrogen gas, really huge fractionation. This hydrogen gas contains 45 to 65 ppm deuterium. This is the most depleted natural substance, what I know in the nature, the geogenic or geological hydrogen. So if we burn this hydrogen, we can get a water of 45 to 65 ppm deuterium content. What about the man-made hydrogen? More and more hydrogen is produced using solar energy. It is produced primarily through electrolysis of water. But if we dissociate all the water, there is no change because all the hydrogen from the water becomes a gas, hydrogen gas. So its deuterium content is the same as that of the starting water. And if you burn this hydrogen gas, you will get back to the original water. This is a closed circle. So in this case, there is no deuterium depleted water, only in the case of the geological hydrogen gas. Fruit juices. Fruit juices contain elevated deuterium. Why? Because the plants evapotranspirate water, and during the evaporation, as I mentioned, the light isotopes preferentially leave the plant, so the remaining water becomes deuterium enriched, also oxygenating enriched, but in this case the deuterium is very interesting. So the deuterium content of the fruit juices is between 140 to 170 ppm, even higher than that of the oceans. Very, very delicious, but it contains higher amount of or deuterium. And what about the plants? Normally, the plants, no matter whether marine or terrestrial, they contain several % less deuterium than the water on which these plants grew. So there is a difference. There is a fractionation. Plants contain less deuterium than the water on which they grow. And in Hungary, I mean the plants in Hungary, contain about 140 ppm. So it means when you consume vegetable, its deuterium content is about this value. Not exactly, but around this value. There are differences between the different plants, of course, but about this one. What about another natural substances? The widely used fuels like natural gas or crude oil are further depleted in deuterium content in respect to the plants because the crude oil and the natural gas is produced from organic material under the surface, but not so depleted as the methane I showed you. The methane is more depleted than the crude oil. Analytical instruments, what we used in our institute. At the beginning, we used a mass spectrometer. This is one mass spectrometer, what we used for measuring the isotopic composition of water. But after a while, a much cheaper instrument appeared on the market. And we used this one. This is a laser analyzer, liquid water isotope ratio analyzer. This is widely distributed all over the world. Now, almost every laboratory uses this instrument because it's much cheaper to buy and much cheaper to run the instrument. The only disadvantage that you can use it only measuring one thing. In this case, water stable isotopes, while mass spectrometer can be used for measuring several isotopes, what was mentioned by Roman Zubarev. So, yeah. And thank you for your attention.
Thank you very much. Thank you very much.